All right, welcome to chemistry. Let's go ahead and get started this morning. Make sure you get out your textbooks, make sure you get out your supplements. I am streaming from home today, so hopefully everything continues to work okay. Um, and things along those lines. I'm actually still under quarantine until Monday, so I'll be teaching from here for the remainder of the week. Um, Past that, go ahead and get out your stuff. Let's get started. If you have not yet put in your name for attendance, please make sure you do so for this class. I need to take my own attendance as well, so please make sure that you do that. I'm still waiting on 2 people. If you have already done it, please don't do it again. I got you. I saw your name and I put it down. But if you haven't done it, please make sure you do so I can go ahead and log that you are here. All right. But we're going to get right into Chapter 5 today. Chapter 5, we're talking about gases now. So we talked before the break about chemical reactions in general. And so while we've talked about the 3 states of matter, we're going to focus in on them a little bit more. Yeah, you guys can actually see the beard today. Normally I've got a mask over it. So yeah, this has been here the whole time. But anyway, Chapter 5, gases. I do occasionally check chat, but I may not be exactly focused on it because I'll be focused on teaching. So just kind of as a heads up. But we're in Chapter 5. We're talking about gases today. And as we look at this, many properties of gases are familiar to you from everyday experience, whether you realize it or not. The air we breathe is a homogeneous mixture of gases, consisting primarily of nitrogen and oxygen. All gases are completely miscible, which means they are able to be mixed, and they actually do naturally do so via diffusion. Okay, so all gases are miscible. Again, that means able to be mixed and naturally do so via diffusion. For example, the odor of frying onions in the kitchen soon permeates the entire house. Gases such as air can also flow from one place to another, as dramatically demonstrated on a stormy, windy day. Gases have mass. Gases can be readily compressed because their molecules are very far apart. Gases expand and contract with temperature changes. They will completely fill any vessel or of any shape into which they are placed. Now, solids and liquids expand relatively little as pressure or temperature is increased. However, a gas is greatly affected by both pressure and temperature changes. Again, this is unlike liquids and solids. And so these points here are really what makes gases gases. It's what makes these states of matter themselves. So you interact with gases all the time. If not, you wouldn't be here. It's called breathing. So you need that ability there. And so a lot of the stuff that we take for granted, even sound, relies on the property of gases. When it comes to your sense of smell, that relies on the property of gases. If someone's cooking in the kitchen, you can often smell it throughout the house. That's the natural of gases naturally mixing through diffusion, so the scent comes to you. You don't have to walk right over to the kitchen to smell it, depending on the thing. But anyway, so that's really what we're talking about here. We're talking about those gases. Its molecules are far apart and will fill the container in which they are placed. As pressures increase, the molecules are forced closer together and collide more often. As the temperature is increased, the molecules move faster and again collide more often. And so as you're going to notice throughout this chapter, the chemistry really happens with collision. That's really what causes it. And so as we increase pressure, as we increase temperature, we can increase reaction. We can increase other scenarios with that. Now, since the volume of gas occupies varies with the temperature and with the pressure, it is meaningless to describe a gas as having a certain volume unless pressure and temperature are also specified. The relationships of pressure and temperature to volume have been described in what are known as the gas laws, and we'll be discussing those throughout the text. The observed behavior of gases as described in gas laws can be explained in part by the kinetic theory of matter, also known as the kinetic molecular theory. And its major assumptions are as follows. First of all, the gas molecules are in constant rapid motion, moving in straight lines until they collide with each other or with a solid or liquid, such as a container's walls or something like that. Gas molecules undergo elastic collisions. In other words, they lose no energy in the collision. I don't remember if we've talked about elastic versus inelastic collisions yet, but oh no, that's a physics thing. So if you were in physics last year, you might remember that. If not, all you need to know is they lose no energy in the collision. The kinetic energy of gas molecules is directly related to temperature. Gas molecules are very far apart and negligible in volume compared to the volume of the gas. Basically, we treat the molecules as if they have no volume. I know it's not actually how this works, but realistically speaking, comparatively, they don't. And then finally, gas molecules have negligible attraction between them. The kinetic theory is literally a moving molecules theory. The central idea is that gas molecules are continually moving about and colliding with each other and with surfaces. A gas that obeys the assumptions of, a gas that exactly obeys the assumptions of the kinetic theory is called an ideal gas. Notice two words in there that should kind of ring bells in your head. First of all, the key word exactly. When in real life does anything ever exactly go as we plan? Okay, just in general, like that's just duh. Okay, so that should already kind of tip you off that we're oversimplifying a little bit. And then second of all, we've gone ahead and called it an ideal gas. Okay, which means it would be what we would expect a gas to react like. It doesn't necessarily mean the gases all behave that way. Okay, so just mentioning that there, this is not how gases really behave, but it's close enough for us to get a lot of things figured out from it. Gases actually really don't behave all that differently from these principles. It's just, they do lose a little energy in the collision when they hit each other. They do have some attraction. They do have some volume, but we use these assumptions and they actually allow us to get very close to what's really happening without having to deal with all the messy math that would go with actually looking at how gases actually behave. Okay, so it allows us to draw general conclusions. And then if you need more specific solutions for a specific scenario, then we would go off that. Excuse me. Now, real quick, before we move on here, we need to discuss a mathematical principle, okay? I know there's a lot of math in the science class. That's kind of why I'm teaching it, okay? But we need to discuss the concept of proportionality. Now, you should have already learned this, especially in geometry, because we talked about it in there. I know because I taught you guys. I know we talked about it in geometry, and I know we've talked about it throughout. We just may not have given it these names. Okay, so this shouldn't be new, but you do need to know what we're talking about. When we say something is proportional, we mean that it is related to each other by multiplication by a constant. And that's a number that has a fixed value in a given situation. And so there are two types of proportions. The first type is called a direct proportion. A direct proportion is a relation in which the value of one variable depends directly upon the value of another variable. A change in one brings a similar change in the other. In other words, if I have x equals ky, and remember in mathematics that k is often used for constant from the German word constant, which actually starts with k. I doubt it's pronounced the same way, but it's very similar. It's just spelled with k instead of a c. Anyway, moving on. So basically, as x were to increase, y would also increase by some constant amount. We don't know exactly what the amount would be, but if x increases, y increases, we can get that much. On the other hand, if x decreases, y will also decrease. That's what we mean when we say direct proportion. If something changes in one variable, the similar change is going to happen in the other variable. Okay, and that's what we're talking about here. Then there is an inverse proportion, also known as indirect proportion. I may use the terms interchangeably. I may also say reciprocal at some point. All the same thing. Okay. This is a relation in which the value of one variable depends upon the reciprocal of another variable. A change in one brings an opposite change in the other. In other words, as x increases, because we're dividing by y, then y will decrease. Or if x were to decrease, y would then increase, okay? Because we would need to increase y to decrease the value of x and vice versa, okay? So just mentioning that there. Notice that k is the same. This could also be rewritten as x is equal to k times 1 over y. You might see that notation in some books. Same idea, okay? But basically the inverse proportion means it relies on the inverse, okay? You'll see opposite changes as we go. And so I know that kind of seems like a weird thing to talk about right as we're starting to discuss gases, but we're going to talk about things being proportional. We're going to talk about this will bring a proportional change to another thing. One other quick thing, because I know you guys probably haven't seen it. The proportional symbol looks like an incomplete infinity symbol. Unfortunately, when I draw it, it also happens to look exactly like how I draw alpha. Okay, but it looks like an incomplete infinity symbol. Let's see if I can, something kind of like that. I can't really draw. Anyway, so just mentioning that there, you'll see it throughout the text as we go, but just wanted to bring that up. All right. So with that under our belts now, let's talk about gas pressure. Okay, 5.2 gas pressure. First of all, one thing to discuss is there's two different kinds of energy, and the first kind is all right, there's two kinds of energy. There's kinetic and potential. For right now, we're just going to focus on kinetic energy, which is energy of motion. There does also exist potential energy, but that's not what we're discussing right now, so we're just going to kind of ignore that, but you guys should remember that from previous science classes. So we're talking about kinetic energy, energy of motion. Real quick note here, your textbook will use the format KE for kinetic energy as a variable. We will not do that in this class. So your textbook does it. All my stuff will say E sub K because I have a real pet peeve of multi-letter variables. Every variable should be one letter, and if you need it anything past that, you use a subscript because that's what you're supposed to do. This is also standard in many physics textbooks. I'm not insane. Well, okay, I am, but we're moving on. Different kind of crazy. Why did this derail? I lost my train of thought. Hold on. Anyway, so that's one of my personal things is, to me, it helps people understand math better is if everything is represented by one symbol, and subscripts to me is easier than two letters. Maybe it's easier to you the other way. Sorry if it is, but we're sticking with this one. Okay, so we're going to use subscripts. So we use E sub K is equal to 1/2 mass times volume. And so when we talk about pressure, actually, hold on, let me go through this. Because gas molecules are in constant rapid motion, they will have kinetic energy, hence why I'm bringing that up all of a sudden. The kinetic energy and thus velocity of a gas molecule depends on the temperature. The higher the temperature of the gas, the greater the average kinetic energy of molecules in the gas, and the lower the temperature, the lower the average kinetic energy of the gas molecules. Now that's important because the collisions of the gas molecules with the container walls constitute pressure, which is defined as a force or a push per unit area. Okay, and so pressure is equal to force over area. Notice that our units then are newtons per meter squared. Newtons would be a unit of force. Area would be in meters squared, hence the units. They just end up combining. And so that would give us pressure. Now, though each individual collision does not produce a large force, the many collisions by each molecule and the large number of molecules present in any measurable quantity of gas generate a sizable force. Hence, you see this balloon is inflated, or the tires in your car are inflated. Yeah, we rely on these little mini collisions to keep your tires inflated on the road. Just mentioning that. Okay, it takes a lot. It takes a lot of pressure to do that, but it does it. Since gas molecules move randomly and are spread out uniformly in any container, the pressure they exert is the same in all directions. For the most part. All right. The SI unit of measure for pressure is the Pascal. Oh, okay. So you'll notice we have the newtons per meter squared. We could have that. So 1 Newton per meter squared is equal to 1 Pascal. Notice that is PA. Pressure is P, so that kind of helps you to remember it. They don't all work out like that, unfortunately, but there you go. Now 1 Pascal is very small, just to give you an idea. For example, here I have your attendance roster. Again, if you haven't put in your name, make sure you do that because I am taking attendance. But I have the attendance roster here. I'm going to try not to show any student data. Okay, the backside is fine. This sheet of paper, if I set it down on the table, I know you guys can't see the table, but if I set it down on the table, that's 1 Pascal. That's 1 Pascal of pressure. The sheet of paper on the desk. Okay, so it's a very small unit, so we tend to use kilopascals. There's a reason. So we tend to use kilopascals there instead because this is, as you can gather, a very tiny amount of pressure. So just mentioning that. So we tend to use the kilopascal instead, much in the same way that we tend to use kilograms instead of grams. Although the gram is useful, we tend to use the kilogram more in everyday. Well, we don't. The rest of the world does. We're moving on. All right. So measuring gas pressure. The pressure exerted by the collisions of gas molecules in our atmosphere with the Earth may be measured by a barometer. This here is one of the original designs of a mercury barometer. Barometers should not be made in this fashion anymore, and we should not be working with pure mercury anymore. I'm just throwing that out there. It's dangerous. But we're going to continue to use it for the sake of illustration. All right. You'll notice that I don't have it in front of you. I have a picture of one because nope. All right. The mercury barometer was invented by Evangelista Torricelli, and I'm sure I just butchered that, in 1643. This instrument, do I have a picture of him? Nope. This instrument is prepared by filling up with mercury a long glass tube that is sealed at one end and inverted the open end in a dish of mercury. So this is not air. It's not an air bubble because it didn't get trapped enough. What happened is this thing was absolutely full of mercury, and then it was submerged without letting any mercury out inside the thing. You typically, when you want to do something like this, you can demonstrate it with water if you wanted to. It is possible to do this. You take a small tube, fill it up with water, and then you put your finger over the end, stick it in a bucket of water, let go. The water should stay in. Now, the water may not stay in because I think water is a lot harder for the atmosphere to hold up the mercury. Don't quote me on that. I'm not getting into it. Okay, so that's probably what he did. Really, again, not ideal. It will kill you. Moving on. The mercury level falls, which leaves a vacuum at the top of the tube, but not all the mercury runs out into the dish. Instead, a column of mercury in the tube is supported by the pressure of the atmosphere on the mercury in the dish. The greater the atmospheric pressure, the greater the height of the mercury column. Since pressure is force per unit area, the diameter of the tube does not matter. As the area increases, the total force on that area also increases so that the pressure is the same. Under the same atmospheric pressure, the mercury column in tubes of differing diameters will be the same in height. Okay? Because its pressure is force per area, it will be the same height regardless of the size of the tube. And so if you want to make really small tube ones so that they're easy and portable, you can without having to increase the scale. The height of a mercury column in a barometer is not constant, but varies with the location on the Earth and with weather conditions. At higher elevations, there is not as much atmosphere above the barometer to push down on it, and the column is not as high. I have to remember, I'm not going to have a bell today. What time do we get out? Oh, 10:50? Oh, I got time. All right, cool. Also, fair weather is generally accompanied by high atmospheric pressure and stormy weather by low pressure. Specifically, storm weathers tend to happen at the boundaries of pressure, not just low pressure, but we're not getting into that because this is not meteorology. All right. Atmospheric pressure may also be measured with using an aneroid barometer, a more compact and rugged type of barometer that senses pressure using a flexible, airtight metal box. I think I actually, no? Okay, I thought I had one. There is a picture on page 62 of your text of that. Typically, most barometers now, they use a vacuum box instead of a mercury because, again, mercury. And the big problem with barometers versus thermometers, because mercury thermometers still sometimes get used and can be used safely. Barometers, due to their very nature, they have to be open to the atmosphere, and mercury can get into the air. So, yeah, it tends to be aneroid barometers now. When the atmospheric pressure increases, the walls of the box are squeezed inward. A pointer attached to the wall of the chamber shows a pressure on the dial. When the pressure drops, the walls of the box bulge outward and the pointer swings the other way. Now, although the Pascal is the SI unit of pressure, scientists often use several other pressure units, and this isn't as simple as English versus metric. This is one of those, several different ones were developed over time. And so while the Pascal is the official one for metric, a lot of times what started being used was millimeters of mercury, because why would you convert it? Okay. So for our purposes, 1 millimeter of mercury, that's the Hg. Hg is a chemical symbol for mercury. 1 millimeter mercury is also known as 1 torr, after Torricelli, who invented the barometer. So it's often a joke in physics and science in general, that the true honor of a scientist is seeing his name in lowercase, because it's been standardized as a unit. Okay, this is what's happened here with torr. So anyway, just mentioning that there. So this is convenient because then you just read the millimeters of mercury. Unfortunately, here in the US, we use inches of mercury, which requires a lot of decimal points to actually be useful, because the inch is much bigger than a millimeter. It's about 253 of them. So, I think that's right. Don't quote me on that. But anyway, so we tend to use inches of mercury, so you don't see the pressure fluctuations as easily. You can switch that sometimes, but we're not getting into that. Anyway, so 50 millimeters mercury, for example, is the pressure required to support a column of mercury 50 millimeters high. Unfortunately, the weight of a mercury column is affected by both temperature and the strength of gravity. Therefore, the millimeter of mercury is somewhat imprecise. So we came up with the torr, and the main difference of the torr is not just as a shorthand. It's actually been redefined in terms of pascals. And so instead of relying on millimeters mercury, which can vary based on where you are on the Earth as far as how your elevation and everything else, aside from just the different air pressure, but gravity affects it too. So that's been defined in terms of the Pascal. It's not exactly equal to 1-to-1, even though I show an equal sign here. That's because, for all intents and purposes, they are equal. It's very close, negligible difference. We're not getting into it. So that's been done to make things more precise. So we'll often use torr in this class. The standard atmosphere is equal to 760. Let's just go into a few other things here. 1 Pascal is 7.5 times 10 to the negative third torr. So there's your conversion factor for pascals to torr. 1 bar is 10 to the 5th pascals. You'll notice that's just shy of kilopascals. It's actually 0.1 kilopascals. No, that's not right. No. It's 100 kilopascals. Goodness. All right, that's 100 kilopascals. So 1 bar can often get used. You might see millibar. There's a lot of units here. Okay, so here are your conversion factors. I highly recommend knowing them. Yeah. Table 5.1 has a more of thing in your book, as far as even more units than what I have on the screen. But the main string you need to know here is 1 atmosphere. Okay, 1 atmosphere worth of pressure is defined to be 760 torr, which is 101.325 kilopascals, which would be 101,325 pascals, because that's how kilo works. Which is about 14.7 psi is the term we would be familiar with pressure. That stands for pounds per square inch. A lot of times here in the US, we'll see PSI instead of that notation. It's the same notation. It's the same thing. It's measuring the same stuff. The reason why I'm not focusing on it, because this is science and we use metric. Okay, so that's the big thing there. All right, so with that in mind, the 760 torr is on average at sea level. So chances are you're not exactly at 760 torr anywhere in the world. That's average. Okay, so if we say standard atmosphere, we mean that. We mean 760 torr. Another unit used for atmospheric pressure, especially meteorology, is the bar, equal to 10 to the 5th pascals. You may have seen weather reports in which atmospheric pressures were given as millibars. Again, 10 to the negative third. The relationships of all these units can be seen in Table 5.1. In this text, the units of torr and atmospheres will be the most commonly used. And you might think that's weird because we tend to focus on whatever the SI unit is. It's just the reality of it is pascals really don't get used a lot. Yes, it's the SI unit. No one cares. It's one of those where everyone else is just like, you know what, we're going to use atmospheres and torrs anyway, make a switch. And no one has. So, and then the meteorologists are like, you know what, we're going to do our own thing. We're going to use the bar. And everyone's just like, yeah, okay. I don't know what to tell you guys. It's kind of a mess. I didn't do it. All right. Now, if we need to measure the pressure of a gas sample, we do so using what's called a manometer, which is used to measure the pressure of gas samples. Now, there's two types. There's open end and closed end. And basically what happens is well, here, let me show you guys. Oh, right, links don't work in here. I completely forgot. And my book's right in front of my taskbar. What chapter is this? 5. You guys get to see me do this live. All right. Not that that's new. Oh, it's already looping. Okay, cool. So what happens is we trap a known amount of gas inside this container. You notice the double valves. I'm going to actually pause this. If you notice the double valves. And so what happens is this side is open to the atmosphere. Excuse me. And because this side is open to the atmosphere is pushing down on this, and you would take an barometer reading alongside your other reading, okay? On average, it's about 760 torr, but you would check what it is in the lab that day as you're doing your experiment, because you need to know exactly what the pressure of the atmosphere is, okay? And then when this gas releases, one or two things can happen. The atmosphere can end up pressing more than what the gas can press through, or the gas will end up being able to press more than the atmosphere. And so this is what that's going to tell us. And so as we open this, you'll notice this is pushed outward. So this is stronger than the atmosphere. So we would subtract the atmospheric pressure from it. No. We would add, hold on. Goodness, I hate it when I do that. We would add it. Yeah, what's wrong with me? We would add the atmospheric pressure to however much this change was, basically, is the issue. There we go. That's the way I'm trying to say this. All right. So, on the other hand, if the atmosphere has greater pressure than what the gas can provide, because at this point now it's not pressing against a vacuum, it's two gases pressing against each other. What ends up happening then is, and I'll wait until it does it again so I can hit pause. All right, basically there. You're not going to let me do it. Stop. Cool. All right, so then you would take the current atmospheric pressure minus the change. Yes. It's minus the change if the atmospheric pressure is stronger. It's plus the change if atmospheric pressure is weaker. That's the way it goes. It'll make more sense as we do an example. So, speaking of, oh, right, the other term. Closed end, on the other hand, requires no adjustment whatsoever. Why on earth did I close my tab? Thank you, Control-Shift-T. All right. But with a closed end manometer, okay, this is a vacuum. And so you just read it and you're done. Okay, so whenever you see a closed end manometer problem, then you're just super thankful that it's closed end and you just rewrite the number. Okay, so let's do a couple of examples. Why did I close it? I'm going to need that again into whatever. The sample of glass in a flask is attached to an open-end manometer. For each of the following measurements, determine whether the pressure of the gas is greater than, less than, or equal to the atmospheric pressure, and calculate the gas pressure if atmospheric pressure right then is 753 torr. So the mercury level on the atmosphere side is 33 millimeters higher than the level on the flask side. Okay, so here's how we're going to do this. Where's my pen? There it is. Okay, so this is going to be my attempt at drawing. Please don't judge. All right. Let's say we have our flask, okay, and then we know we're going to have something along this shape. All right, so let's say here we know this is 753 torr to start, and then the mercury level on the atmosphere side is 33 millimeters higher. So we know between these two, this side is up 33 millimeters. Okay, which means the side is also down by 33 millimeters, but that's beside the point. So since the mercury is higher on the atmospheric side, we know that the pressure of the gas is greater than the pressure of the atmosphere because the gas is able to push more than the atmosphere is able to push. So because of that, based on that formula, the pressure of the gas is equal to the pressure of the atmosphere plus the reading. Pressure read, I guess? I don't know. I don't normally give it a subscript. All right. And so that's how we figured this out. And so the pressure of the gas then is equal to 753 plus 33, and we get 786 millimeters, or sorry, torr. We use torr in here. Millimeters of mercury or torr. Okay. And so that would be our answer. Now I'm going to go through right now and switch it over to the pre-done math. Okay. And basically that's the comparison is we look at which one is bigger than which, and then pick plus or minus based on that. Now let's say we have a different sample of gas. Okay, but everything else is the same. Except now the mercury level on the atmosphere side is 45 millimeters lower than the level on the flask side. So now in our drawing, and I'll redraw it over here. Okay, the millimeters is down. It's down 45 millimeters on this side. So that means the pressure of the atmosphere must be greater than the pressure of the gas. Okay, so I know that the pressure of the gas must be less than the pressure of air, is often how we'll word that, because it's not able to push as hard as the atmosphere is able to push. And so then we subtract. So we take 753 minus 45, and we get 708 torr. I'll give you guys just a moment to copy that. All right, let's go on to example 5.2. My mic's working, right? Okay. Example 5.2, the difference between two mercury levels and a closed-end manometer is 345 millimeters. What is the pressure of the gas? Don't overthink it. It's 345 torr. If it's closed-end, you don't have to worry about it. Okay, so you have to pay attention to which type of manometer it is, because I've had too many people tell me there's not enough information. It's closed-end, you're done. It's 345 with torr at the end. That's it. Sweet. These are my favorite kind of problem. It's super easy. Okay, you'll notice on the screen just appeared a link to a crash course video. Obviously, I cannot show those. Okay, so I highly recommend, as basically your only homework today, is to go through and watch Crash Course Chemistry 12, The Ideal Gas Law. I would love to show it to you guys in class. I just can't do that from here. Past that, keep in mind, make sure you're working on your Chapter 5 homework. It's obviously not due tomorrow or anything like that. I mean, it's Wednesday, first of all. But anyway, so there's that. And then the other thing I want to mention, oh, yes. You guys were supposed to have a test right before we ended up shutting down. Okay. So the way we're going to do that is we're supposed to be back on Monday and Tuesday. Okay. We're starting next week. And so that test will be Monday, Tuesday, but it will be open book. Okay. And if you guys need more than the 2 class days to do it, you guys will have the study hall periods as well. Real quick, if you are not a regular distance learner and you will not be there on Monday or Tuesday, you need to let me know by email. Okay. And the reason for that is so that way I can set you up with an account so you can take the test remotely. Okay. I use a different site for that because that site allows me to do a lot more control over the test as far as how it's taken and things like that. So even though it'll be open book and things, I'm still going to use that site because it's already in there. I was ready to go for it. And then that. So just mentioning that there. Can you all still hear me? Hope so. Because YouTube's complaining about my bit rate. I don't know. Anyway. So with that in mind, just let me know if you're not going to be there Monday or Tuesday of next week. So that way, oh good, you guys can still hear me. Okay, YouTube's just on something then. Just make sure you guys let me know that if you're not a normal distance learner. If you're a normal distance learner, I'll send you the link on Monday like normal. But if you are not a normal distance learner, I need to get your account set up for you. So please let me know. So that way we can do that. So we'll just take that when we get back on Monday and Tuesday. That's easier than me getting everyone set up with an account for one test. So we'll just take it like normal. So I'm just kind of starting chapter 5 because what else are we going to do? And then you guys will take that test as an open book test. You don't have to study extra for it. I would make sure you're still familiar with the material. Obviously open supplement too, by the way. Anytime it's open book, it's both. I don't normally like giving them, but this is extreme circumstances of we were supposed to have it before Thanksgiving break, and then we were supposed to have a little time this week, and then we lost 2 more days. So rather than continuing to lose class time, we're just going to take it as open book and application. All right. One last thing here on the bottom of page 64 in your text. Just mentioning this. The gas pressure thing explains why a taller straw makes it very hard for you to get a drink out of there. It's got some very creatively drawn animations. It's at the very least, not animations, that's the wrong word. Picture there. So just mentioning that, if nothing else, it's funny, but it explains why a longer straw is harder to get stuff out of a drink. The entire reason for that is because you're relying on atmospheric pressure to help you. And then the longer it is, the further away you are from where atmospheric pressure is. And so you have to overcome all that distance instead of just a little bit. So that's why that's the reason why straws tend to be on the shorter side. That's why crazy straws are so hard to drink out of, because you're lengthening the tube. It's just not straight line. So anyway, hope that's helpful. I don't know, but there's a real life application of it, if you will. We will get into the actual gas laws, Lord willing, tomorrow. And I say Lord willing because who knows what's going to happen between now and then. Again, I highly recommend you go through and watch that crash course in preparation for tomorrow. Because that will actually be talking about tomorrow's lecture. So that would be introducing tomorrow normally, is what I would use it for. And unfortunately, I just can't do that. Okay, so we'll talk about the gas laws tomorrow. And then I will see you guys later. So here's what's going to happen. It is Crash Course Chemistry number 12. It's Crash Course Chemistry number 12. That information is actually... Oh, it was on the screen. It's on my screen. Here. There you go. It's Crash Course 12, the ideal gas law. That's the one you guys want. That information is also at the beginning of your supplement. After we talk about 5.3, there are actually 2 Crash Course videos I recommend you watch. Number 13 will help review over it as far as the problems with the ideal gas law. Yeah, okay, in case you haven't gotten this already, I've kind of been leading up to it. There's quite a few problems with it, but it works well enough for us to get by with it. So you have the ideal gas law, and then you have the problems, and then we'll talk about real gases, at least a little bit. Unfortunately, I normally just let the video talk about it, so I might just let you guys know, hey, go watch this. All right, that's going to be where I sign out. So what's going to happen is I'm going to end this stream, and I'm going to restart the stream up at the school, so that whoever your next teacher is, who is your next teacher? Oh, Mr. Larson. So he can just stream from there like normal. So everything there will be normal. I'm doing this because, again, my quarantine period is not over. I actually had COVID over the break. I'm fine. It was, and I know it affects everyone differently, and I'm grateful and blessed that it was minor for me. And I'm fully aware of that. But to me, it was just like a mild cold. So that's the thing, but I don't want to pass it to anyone because, again, everyone reacts differently to this thing. And so that's just my thing there. So I will see you guys, Lord willing, on Monday, because by then my quarantine period will be up. It's just, for right now, I'm stuck kind of staying at home, which is also why I can't fix some issues right away. I'm trying to fix stuff from here. It's not exactly easy. So anyway, so I'm trying to fix stuff from here. I'm trying to teach from here so that way you guys don't miss out. But also so that way everything else gets done. So I will see you guys, Lord willing, on Monday. Yep, there's one. And in the meantime, I'll be back here tomorrow. See you guys.